All right, so this is example 2.4e, and it's labeled holding up a pole with 3 cables, and it's part of chapter 2. So it will use vectors in ease, and it will also go through building a vector plot, which is what we just talked about. So here's the exercise. You can see there's a 5-meter pole that is meant to be held up by these 3 cables, 1, 2, and 3. And 2 of the cables have already been set up. So that's cable 1, which has a 2 kilonewton tensile force in it. And you can see the end points of cable 1 are given, D and A. And then cable 2 has a 1.5 kilonewton force in it, and it's also connected to D, but it's connected to the ground at point B, and points A and B are set. So we're supposed to determine where to attach the 3rd cable. So where should point C be on the ground, and what the force in this cable should be, such that the resultant, or the summation of these 3 forces, 1, 2, and 3, is vertically down. So straight through the axis of the pole, and has a magnitude of 5 kilonewtons. So that's the problem. Once we get the problem completed, we can visualize these forces with a 3-dimensional vector plot. So that's part B. And then part C asks what would happen if cable 1 snapped. So in that case, what would the resultant force look like? And then specifically, what would be the component of the resultant force that is perpendicular to the pole? And that's obviously the component that would be troublesome, because it would be trying to pull the pole over. So that's the exercise. So maybe you want to go off and try that on your own. And once you've solved it, or at least tried to solve it, come back and we'll go through the solution together. Alright, so as usual, before I try to program the solution, I'd like to know that I have all the equations sort of figured out. Programs, again, all they do is solve equations for you. It's up to you to come up with the equations. So let's go through at least a roadmap for the equations that I need. So you can see that points A, B, and D are all given to us, so we can enter those, and those are then known, those coordinates. I think the next thing I'm going to do is define position vectors that correspond to these 2 cables that are known, so cable 1 and cable 2. So RDA is just point A minus point D, and RDB is point B minus point D. And those define the directions for forces 1 and forces 2. So because I know the directions and the magnitudes, I can actually define vectors for force 1 and force 2. So that'll be the next thing I do. Force 1, the vector, is the magnitude of force 1 multiplied by the unit vector that is in the direction of RDA, and force 2 is the magnitude of force 2 multiplied by the unit vector in the direction of RDB. So those 2 vectors are now known. The other vector that I know is what the resultant force needs to be. So the resultant force needs to be 5 kilonewtons in magnitude, and it needs to have a direction straight down, right, straight along the pole's axis, which is minus k. So I would define the vector corresponding to the resultant force. And then the resultant force is the sum of these 3 cable forces, F1 plus F2 plus F3. The sum of those vectors equals the resultant force. And so if I look at this equation, the unknown vector then is F3, so I would go ahead and calculate F3. So this is now going to tell me the vector force that I would need to apply in that 3rd cable. So the vector force is going to give me the magnitude that I need, which is part of part A. The other part of part A is asking, where on the ground is point C. So where do I need to connect this force to get the right resultant force? So let's see. I know that point C is the result of a cable that starts at point D and travels in the same direction as this force vector F3. So point C then is going to start at point D, and then I can add to point D a length, the length of that cable, and multiplied by the unit vector that defines the direction of the force 3. So that's what I've done here, right? C is just starting at point D, and then the second part is the length of that cable, and then this is the direction of the cable. And if you think about this, this is one equation in terms of vectors, but every component of this equation so every direction has a component, right? There's going to be actually three equations associated with this, which is C sub x is D sub x plus the length, and then the x component of the unit vector, C sub y, and C sub z. So these are three equations right here, and actually in four unknowns, right? I don't know C sub x, C sub y, and C sub z, right? I don't know the coordinates of that endpoint, and I also don't know the length of the vector. But the last thing that I do know is that point C lies on the ground, which means that C sub z actually has to be 0. So these four equations right here, these are four scalar equations in four unknowns, or this equation plus this equation is also four equations and four unknowns. So I know I have enough equations, and I can go ahead and then proceed to solving the problem. Alright, so solving the problem in ease is really just translating these equations into equations in ease, and sort of going slowly and trying not to make mistakes, checking units and all that kind of stuff. So first I'm going to start with the points. There's 4 points in the problem, A, B, C, and D, and they are all vector variables in the sense that they all have 3 coordinates. So I'll go ahead and define them all to be 3-dimensional vectors. So that's what this dollar vector statement does. 3 of the 4 points I know their coordinates, so let's go ahead and assign them. So A is vector assign, let's see, it's -1, 3, 0, because it's on the ground, and that's in meters. B is vector assign -2, -3, 0, so that's the other connection point on the ground. And then D is the top of the pole. The top of the pole is 0, 0, and it's 5 meters high. So we can solve, we can look at those, make sure they look okay, make sure the units are okay. And then let's move on to the position vectors that correspond to each of the cables. So there's 3 cables, and they each have position vectors. So it's RDA, RDB, and if I needed it, RDC, right? So those are going to be defined as vectors, and 2 of these 3 I can actually calculate. RDA is just point A minus point D, and RDB is point B minus point D. So those are the 2 position vectors that define the directions of those 2 forces. So there's 3 forces from the cables. Those are also vectors, so I'm going to define those 3 forces to be vectors, F1, F2, and F3. And again, 2 of those I know right away, because I know the direction and the magnitude of those 2 cables, F1 and F2. So F1 is going to be 2 kilonewtons, that's the magnitude, and then I multiply that by the unit vector in the direction of RDA, which is just RDA divided by the magnitude of RDA. And same thing for F2. Right, F2 has a magnitude of 1.5 kilonewtons, and it's in the direction of RDB. So it's RDB divided by vector mag RDB. All right. I said I also know the resultant vector. I want to have R be the resultant vector, so I'm going to declare it to be a vector. And I know that that vector is straight down. So this is vector assign no component in the x, no component in the y, and then -5 kilonewtons straight down. And then I get F3 by realizing that R is just the sum of F1 plus F2 plus F3. So this is going to give me vector F3. And if you think about this, this is really 3 equations and 3 unknowns, right? One for the x, y, and z component of F3, but it gives me the the vector F3, and I can look at it, and this is that vector that I need in order to get the resultant force that I want. If I want the magnitude of F3, it's as easy as taking using the vector mag function here, and that tells me that the magnitude of F3 is 2.268 kilonewtons. So that's the tension that I would need in that cable. And of course, the last thing I need is the connection point. So we said that point C is given by point D plus the length, so L3, multiplied by the unit vector in the direction of F3. So that's this equation right here. And we could break that into 3 separate equations, but because we can use vectors in these, we don't have to. We can just write that vector equation. And what you find then is at this point you don't have enough equations for the number of unknowns, and that's because the last thing we need to specify is that the z component of point C, the z coordinate to point C, must be 0 so that C is on the ground. And we put that in and we solve, and you can see that here's the connection point, right? C has to be at x equals 1.970, y equals minus 0.6789, and of course z is equal to 0. And that's the solution to part A. Part B asks us to make a 3D vector plot of these 4 forces. So we'll go ahead and select a new plot window from the plots menu, and then select vector plot to bring up this vector plot dialog. We want to use 3D vector plot. Right? We want to see this in 3 dimensions. And then one by one, we're going to plot these 4 forces. So I'll pick F1. I want them to emanate from point D, just to make it a little easier to look at. And I'll hit plot, and I'll go ahead and pick F2, keep the same origin, hit plot, F3, and finally R, and then I'm done. And at that point I have this 3D vector plot that shows these 3 forces, and it then shows that R is straight down, as I knew it should. So that's a nice way to visualize these forces. Alright, finally part C asks us to figure out what happens in the event that one of these cables snaps. So we're going to have to modify our ease code, and depending on what kind of license of ease you have, that will require either that you save and then copy it and make a new ease code so that you can modify it without messing up your part A, or if you have a professional version, you can just add a tab to your equations window. So that's what I'm going to do here. I'm just going to click on the main tab and select add a tab, and I'll call this tab part B, and then I'm going to copy all of the equations I have in main into part B, and so I can work on this, and if I want to go back to part A, I just go back to the main tab, which is really pretty convenient. So in this part B tab, or I guess it's actually part C, sorry, in this part C tab, I need to make a couple of changes. The first one is pretty obvious, and that is that if cable 1 snaps, then the force associated with cable 1 is 0. So let's go ahead and change the magnitude of this force from 2 kilonewtons to 0. And then the second thing I need to do is specify the F3 is exactly what it was calculated to be in part A. So if I go back to the main tab, I can see this is the vector F3. So we will just use this same vector in our part C tab, and assume then that cable 3 is exerting the same force that it did before cable 1 snapped. And then finally, I don't anymore know what the resultant force is going to be. I'm actually calculating that. So let's get rid of this specification of the resultant force, and then we'll just calculate it with this equation that the resultant force is F1 plus F2 plus F3, and F1 is now 0. So if I solve, I find out that this is the resultant force, and it's changed directions. It's no longer straight down. The question asked us to figure out the component of R that is perpendicular to the pole, so the component that's trying to pull the pole over. So the first thing I'm going to do is figure out the component of R that is parallel to the pole, and you do that by taking the dot product of R and a unit vector in the pole direction. So a unit vector in the pole direction, we'll call that u. So I'm going to define a vector u, and I'm going to define u to be minus vector unit k, so minus the unit vector in the k direction. And then I'll get the magnitude of r parallel to the pole using the vector dot function operating on the vector r and the vector u. And if I want the vector corresponding to that that component that's parallel to the pole, it's as simple as multiplying the unit vector u by its magnitude r parallel. And this is, of course, not surprisingly, just the z component of the resultant force. If I want the component of r that's perpendicular to the pole, I just realized that r is equal to the summation of r parallel plus r perpendicular, and I know r and I know r parallel, so I just get r perpendicular, and that's what I've done here. If I want the magnitude of r perpendicular, I just use the vector mag function, and I find out the magnitude of the perpendicular force is 1.069 kilonewtons. So I have 1.069 kilonewtons that's pulling on this pole sideways, basically trying to tip it over. And I think that is everything we were asked to do in this exercise.